Sometimes chemical reactions involve two or more steps that happen one after the other. Even though the balanced equations are often used to show what is reacting and what's produced, the details may be a little bit more complicated. The reaction mechanism or reaction path provides details regarding the precise step-by-step process by which a reaction occurs. Often these involve elementary reactions. This means steps. For example, the decomposition of ozone, which is commonly represented by this equation, actually has a reaction mechanism that includes two steps. Each of the steps in a reaction mechanism is an elementary reaction. Notice that the oxygen atom produced in the first step of this mechanism is consumed in the second step, and therefore does not appear as a product in the overall reaction. Species that are produced in one step and consumed in a subsequent step are called intermediates. Intermediates are never represented in a balanced equation. They're usually very unstable. And unlike balanced equations representing an overall reaction that may actually be the result of several steps, the equations for elementary reactions are explicit representations of the chemical changes taking place. The reactants in an elementary reaction's equations undergo only the bond-breaking and/or bond-making events that are shown. Here's an example. We have 2 moles of nitrogen monoxide reacting with oxygen to form 2 moles of nitrogen dioxide gas. The reaction shown by this overall equation actually occurs in 2 elementary steps. First, 2 moles of nitrogen monoxide combine to form 1 mole of dinitrogen dioxide. The dinitrogen dioxide then goes on to react with oxygen to form 2 moles of nitrogen dioxide. If we added up these elementary reactions, we would get the overall reaction. Notice that the dinitrogen dioxide is an intermediate. It is created in one step, but used up in the next. For ordinary chemical reactions, you can generally only determine rate laws through experimental data. You may also need to do experiments to figure out if there are elementary reactions going on and what these are. However, for elementary reactions, you can derive the rate law directly from the balanced equation. You can also often determine which of the elementary steps is the rate limiting step. But remember, you can only do this if you know that a reaction is an elementary reaction. For any elementary reaction of this general form, where you have A and B being the reactants, D and E being the products, and little a, little b, little d, and little e being the coefficients, we can form a rate law. Rate equals K, concentration of A to the little a, concentration of B to the little b, where A and B are actually the stoichiometric coefficients. This will make more sense in an example. Let's consider the following equation. Nitrogen dioxide plus carbon monoxide yields carbon dioxide plus nitrogen monoxide. If this were an elementary reaction, we'd predict a rate law of this. Rate equals K times the concentration of nitrogen dioxide times the concentration of carbon monoxide. But the rate law has been experimentally found to be rate equals K times the concentration of nitrogen dioxide raised to the second power. Since our experimental rate law does not match our predicted rate law, we know that this reaction must have more than one step. Chemists use a combination of the experimental rate law and intuition or educated guessing to determine elementary reactions. Here's an alternative 2-step reaction that could explain this rate law. In step 1, we have 2 moles of nitrogen dioxide decomposing to form nitrogen monoxide and nitrogen trioxide. In step 2, the nitrogen trioxide combines with carbon monoxide to form nitrogen dioxide and carbon dioxide. And as you can see, if we added these two elementary reactions up and crossed out the common species on both sides to simplify our equation, we would get the overall equation that we started with. We see here that nitrogen trioxide is an intermediate, so it does not appear in the overall reaction. The two elementary reactions add together to give the overall reaction. Now, if we look at our elementary reactions, we would see that if we used the coefficients and the species from the first reaction, we would get our rate law, where our rate equals K times the concentration of nitrogen dioxide squared. And you may wonder, why doesn't step 2 contribute anything to the rate law? Well, now we have to talk about rate limiting step. Often the rate of one of the elementary reactions is slower than the rate of the other elementary reactions in a process. The slowest step is called the rate limiting step or the rate determining step, and any subsequent steps have to wait for the slow step to happen before they can proceed. Here's an analogy. Imagine you're pouring water into a series of funnels. The slowest funnel, in this case the smallest funnel, is going to determine how fast you can get the fluid in. In this example, the small funnel is the rate limiting step. The liquid won't go into the larger funnels until it's passed through the smallest funnel first. The overall reaction rate is determined by the rate of the slowest elementary step. And we call this the rate limiting step or rate determining step. And if we take a look at the rate laws for these elementary reactions, and remember we can make our rate laws based on the coefficients because we know these are elementary reactions and we can do that, we find that only the first one has a rate that matches the experimentally determined rate. Hence, we know that step number 1 has to be the slow step, and the rate of the overall reaction is determined by this step. Some elementary reactions involve one species, and some involve 2, and some involve 3. The number of reactant species, whether they're atoms or molecules or ions, that participate in the rate limiting step is called the molecularity of the reaction. In unimolecular reactions, a single species decomposes or rearranges to result in one or more products. And here is an example of how that might look as an equation, and how our rate law would be K times the concentration of A, just a nice first order rate law. We could also have a bimolecular reaction, a reaction involving 2 reactant species, such as this one where you have A plus B going to some sort of product. Our rate law here would be K times the concentration of A times the concentration of B, and each of these would be raised to the first power, and our reaction would be second order overall. We could also have a bimolecular reaction where you have 2 identical species reacting together to form products. Our rate would be K times the concentration of whatever that species is squared, also a second order rate law. Termolecular reactions involve the simultaneous collisions between 3 reactant species. They're uncommon because the probability of 3 or more things colliding simultaneously is very rare. However, there are a couple of these reactions that are known to occur, such as this one between 2 nitrogen monoxides and oxygens to yield 2 nitrogen dioxide. And our rate law here would be K times the concentration of nitrogen monoxide to the second power times the concentration of oxygen raised to the first power. Since 2 plus 1 equals 3, the overall order of this reaction is 3. In summary, the rate law of an elementary reaction can be inferred from the stoichiometry of the molecules participating in a collision. Elementary reactions involving the simultaneous collision of 3 or more particles are rare.